polynomials of degree less than or equal to 2, right? Is there any other set which can you think of any other object which behaves in this way? So this is one example that I am starting with. Another one. Give me another example. Something which you are familiar with. So you understand the behavior, right? You have a set of some objects. In this case, the object was a polynomial of degree less than or equal to 2. Take any two such polynomials, add or multiply with a scalar, you still get the same thing back. Have you seen anything else which behaves in this way? Any other mathematical object which behaves in the same way? Remember the title of the course? If you look at a matrix, let us say define M as a set of all M cross N matrices. When you add two such matrices, what do you get? Yes, somebody has already written matrix. See, when you add two such matrices, what do you get? You get another M cross N matrix. Multiply a matrix by a scalar quantity, what do you get? Again, you get another M cross N matrix. Same behavior, right? So this also exhibits the same behavior. Like M1, M2, element of M. M1 plus M2 is also an element of M. And some A times M is also an element of M, where A is a real number. I'll be restricting myself to all real quantities. Unless I say specifically it is real. What about one more example? Something which is slightly different. Vectors. What are vectors? We haven't defined vectors yet, so let us not talk about vectors. See, we saw polynomials, we saw matrices. Now let us look at something different. Let us look at functions. Okay. So consider the set of all, say, continuous functions. Say I am defining functions whose domain is from 0 to 1. That means let us think of f. T is an element of closed interval 0, 1. That means I am defining functions which go from t is equal to 0 to t is equal to 1. And I am thinking about all continuous functions. In that case, when you add two continuous functions, what do you get? Will the continuity break when you add? No. It's just a linear operation, right? When you add two continuous functions, you still get a continuous function. You multiply a continuous function with a constant, you still get a continuous function. So this set, like if you say set of all ft such that ft is continuous, this set also exhibits the same behavior, right? Fine? You have some question? Okay, yeah.
So can you give an example that it does not follow this, which closure is not?
I'll come to it. I'll give you some examples. Okay, let us take the case of all. So you're saying polynomials of exactly degree 2. In that case, what will happen? I'm saying that in that a2x squared plus a1x plus a0, I'm saying that a2 is not equal to 0. But then when you add two such polynomials, see I add x squared plus x plus 1 and minus x squared plus x plus 1, I end up with 2x plus 2. In this case, so my original set is set of all polynomials with degree 2, but addition will give me a polynomial which is of degree 1, which will not belong to the set. So closure is not satisfied. Fine. So that's why I said in the first example, it should be polynomials of degree less than or equal to 2. If you remove that less than, then it will not work. If you say it is equal to, then it will not work. Fine. Okay, so I have given you 3 examples where the elements of the set is such that you add 2 elements, you still get the same element. You multiply an element with a scalar quantity, you still get the same element, right? And so there is a property that you're seeing. So this, when you see such a common property, what you tend to do is you try to abstract it, like saying, okay, let me take this behavior and define a new object. And the new object that gets defined is called as a vector space, right? So I've given, so from these examples, can you guess what all things should be there in a vector space? I gave you 3 examples and I'm saying that vector space is an abstraction of these 3. I gave you 3 completely different examples, but the behavior can be captured by one notion of vector space. And that is, this is what is called as abstraction. You see a common behavior and you say, I define a particular object which captures the behavior of all these 3. So that I don't have to examine each of them separately. I only need to learn how a vector space behaves, then I know how to handle polynomials, I know how to handle functions, matrices, everything. Right? Now, looking at these 3 examples, can you tell me what all are involved in defining a vector space? Abstract it. This is known as the process of abstraction. What is needed in abstracting it into a vector space? What all did we talk about here? See, in all the cases, I started by defining a set. I started by defining a set of polynomials. Then I said there's a set of matrices, there's a set of continuous functions. So that underlying set is there, right? So you need, so I'll give you the formal definition. So there is a set V, okay? This is a set and it is called as a set of vectors. So notice one thing here, vector is a general term. As of now, at this point of time, whatever notion of vector you have in your mind, erase it. Because vector is a general notion. So whenever I say vector, don't think of an n tuple, okay? Don't think of a column vector as of now, because from the 3 examples that we saw that in the first case, a vector was a polynomial, second case, a vector was a matrix, and third case, vector was a continuous function. So vector is a general object, fine? Don't associate any structure to it right now. So what I start with is a set V, and I call the elements of this set V as vector. What else did we talk about? Huh? Yeah, we talked about 2 operations, right? Because I talked about addition. Addition was for which elements? What did you add? Yeah, you added elements in P. You added 2 polynomials, you added 2 matrices, you added 2 continuous functions, right? So addition is for elements of the set V. So this is vector addition, right? Because you are adding 2 elements in the set V and you are saying that after addition it will still be back in the set. That part I'll come to later. Now then, what else is there? 2 operations we talked about. One is addition and the other is multiplication by a scalar. So what all do you have to define now? Scalar. From where does the scalar come? Right? The scalar has to come from somewhere, and scalars typically come from a mathematical object called as field. Okay. Scalar comes from a field. I will define what a field is if you are not familiar with it. And then we had another operation which is scalar multiplication. So I'll indicate with dot. This is scalar multiplication. What is a field? In a very, very crude definition of field would be what? Field is a set, okay? Field is a set with 2 operations. In a very crude manner, what is, I don't want to go to the formal definition of field, but in a crude manner, what is a field? Yeah, what is a field? It is a set along with 2 operations. It is typically called as the operations are called addition and multiplication. Fine. So, what is the definition? Here we need a little bit of abstract algebra. So instead of going to the definition, what I'll tell you what it is. It is, in a very crude manner, it is set in which you can do addition, subtraction, multiplication and division. All the 4 operations you can do. You can add, you can subtract. Subtract is actually the inverse of addition. You can multiply and you can do the inverse of multiplication, which is division. Fine. So examples, so in this course we will, so you can say you can multiply, divide, add and subtract. So a set in which you can do all this is called as a field. Basically, for people who know abstract algebra, it is an abelian group under addition, it is an abelian group under multiplication. That is a field. Fine. If all these terms are new to you, don't bother, because for us the fields I will restrict to R or C. Set of reals. You can add, you get a real number. You can subtract reals, you can multiply reals, and you can also divide, right? Addition, multiplication, division, what else is there? Subtraction. Everything is possible in the set of reals, also in the set of complex numbers. So for us the field will be R or C, which means our scalars will always come from either R or from C. But keep in mind, in general it can be anything, any field, right? But we will restrict to only R or C. Fine. Having these 3, like, so V, F plus and dot. These 4 objects together is the vector space, provided some conditions are satisfied. Okay. I mean, just because these exist, it doesn't become a vector space if the following are satisfied. Questions? Any questions?
Why is R a field? Because there are some undetermined forms in R, like 0 by 0 or infinity by infinity.
No, it is an see, when you say addition, multiplication, etc., division by 0 is not there. In the definition of group, there is no division by 0. So there are no indeterminate forms. Because you talk about inverse, whenever you are saying that it is an abelian group under multiplication, inverse exists for every element other than 0. That is by definition of group.
And 1 is for infinity also.
And infinity is not even considered as a number. It comes in the limit process, right? It comes as a part of limit process only, not as a process of normal addition or multiplication. Questions? Okay, so if there are no questions, I'll go on to the properties. First one is closed under addition. How will I write it mathematically? I'll use x, y, z to represent elements of V or vectors, and alpha, beta, gamma to represent elements of field or the scalars. So when I say that it is closed under addition, addition is vector addition. How do I write this? Mathematically, how do you write this? Come on. Huh? X plus y. So you have, I'll start with x, y, z, element of V. That means x, y, z are all, they are vectors. These are 3 vectors. So when I say that the set V has to be closed under addition. Closed under addition means V is closed under addition. What does that mean? Closed means what? Yeah, when you take 2 elements and you add this, the sum should also lie in the same set. So xy is an element of V, x plus y should also be an element of V. When you take, that is what we saw in the beginning, right? You take 2 polynomials, add, it will come back to the same set. That is being closed under addition. Fine? Then I'll say 1a and 1b. 1b would be what? It should be closed under addition, and then what it should be? Closed under what? Under scalar multiplication. So you have alpha element of f, x is an element of v, alpha into x should be an element of where? V. You take two elements from the set of vectors, add them, it should still be a vector. You take a scalar and multiply it with a vector, you should still get a vector, right? So that is what you're saying. I mean, mathematically that means it is the set V is closed under vector addition, the set V is closed under scalar multiplication. In this case, the scalar comes from the field. Is that clear? Okay, in addition to these two, I mean, this is a basic necessity for this. The properties, like, have you people finished writing? Additional, okay, so additional properties are, say I have x, y, z element of V. Any guesses? X plus y should be equal to y plus x, commutative property. Then x plus y plus z should be equal to x plus y plus z, right? Associative. Then wait, distributive will come. Existence of identity, that is you have x plus 0 equal to x. So this 0 is a 0 vector. Okay, remember that you have got two sets. You have got a set of vectors V and you have got a field F. There is a 0 present in the set of vectors and then there is a 0 present in the scalars also, field also. So initially I'll just put V here to indicate that this is the 0 for the set of vectors. Then guess what would be the next one? Existence of inverse, right? So for every x element of x, there exists minus x element of V, sorry, this is V, such that x plus minus x is 0 vector. Fine. There exists a inverse for every vector. So these are the four properties with respect to vector addition. Now you need other properties, right? There is something else also. We have only looked at one operation, which is vector addition. There is a scalar multiplication part also. So what all do you expect there? What?
X plus alpha y equal to alpha x plus 1.
X.
Coming from here, it's
Wait. Okay, the next of properties are, say, let us take alpha beta element of f, x y element of v. So I'll write something here. Tell me what is happening. And okay, but there is something interesting here. What is interesting here? If you look at the first expression, if you look at this, tell me, what do you observe here? I mean, though it looks like a harmless equation, there is something that you have to observe here. What is it that you observe? These two equations are in that way a little bit special because there is something that you need to observe here. What is it?
the order.
No.
I mean, the way alpha beta are appearing.
We can express one vector with different magnitudes.
That is basically an interpretation, but if you observe this expression, How many multiplications do you see here? Huh?
One scalar and one
How many multiplication? How see in this equation? If you see, there are
One scalar multiplied. Only two scalars are multiplied.
see if you look at this product alpha beta, where does this happen? It happens in the field. There are two different types of multiplications in this. The first in the product alpha into beta, this multiplication is actually the field multiplication operation. They are two different operations.
Okay.
This is a field multiplication, whereas this is the scalar multiplication, right? So there are two types of multiplications. Here this is the field multiplication and this is the scalar multiplication. So now you can see what is interesting in the next expression, right? What is interesting in the next one? Where does this plus lie? This plus is a field one. I'll write F here to indicate that this addition is the field addition and this addition is the vector addition. Though I have used the same symbol, understand that the meaning is different. In this case, the meaning of this plus is this addition happens in the field, whereas this addition is actually the vector addition. They are two different operators. Be mindful of that. But when we write, we typically don't care about it because we understand what it is. Fine? Is that clear? Yes or no? And this is like how the two, operate with each other. Scalar multiplication and vector addition. It is alpha into x plus y is how it is distributing. Dot distributes over plus alpha x plus alpha y. And one is what? One has a meaning. Okay, this is identity of field. Identity of field multiplied by the vector will give you the vector back. Right? So this identity is actually the multiplicative identity. There are two identities. There is additive identity and multiplicative identity. So the multiplicative identity, so even though I write 1 here, be mindful, okay, somebody can give you a very general field. There it is not going to be the number 1, it is going to be the multiplicative identity. Be very mindful of this because I can create questions where your multiplicative identity is not 1 and something else. So keep this point in mind. These are all ways by which people can catch you. So don't think of it as a number 1. That 1 means it is a multiplicative identity of the field. If the multiplicative identity happens to be 2, you will have to think of it as 2 into x. It depends upon the field, whatever field you are defining. Okay. If you are looking at C or R, then you don't have to worry, it is 1. But I can cook up any field. Is that clear? You have some question.
I'm just trying to understand, this one means, I'm coming from engineering background, so I'm trying to understand whether this is the vector you're talking about.
No, this one is from the field. It is scalar.
Scalar.
Yes. Because see, this dot is actually the scalar product. The scalar multiplication. So when you're multiplying, when you're doing scalar multiplication, the scalar comes from the field. And this, the number 1, here even though I wrote it as 1 because typically that is a way to write. But even when you write 1, understand that it is actually the multiplicative identity.
But in that case, right hand side will not become x, right?
It will become x itself. That is a meaning. The meaning, see, that is why it is written as a property. You are saying that whenever you take the multiplicative identity of the field and multiply it with a vector, you should get the vector back. It doesn't matter whether it is number 1 or whatever it is. If I call it as E, if I call that the multiplicative identity is E into x should give me x back. Fine. Okay, now examples. The formal definition is over. You have to give me examples of vector space. So whenever, remember, the moment I say vector space, what should come to your mind is these 4 objects. A V should come, an F should come, a vector addition should come, and a scalar multiplication should come. These 4 objects together defines a vector space. There are two sets here. There are 2 sets and 2 operations. One is a set of vectors, the other is a set of scalars, which is a field, and then there is a vector addition, there is a scalar multiplication. So, I mean, from now onwards, the moment anyone says vector space, these four things should come to your mind. You should be always mindful, okay? What will happen is eventually you'll forget about all the remaining things and we'll remember only V. But then always remember that there is an underlying field. Without defining the underlying field, the vector space is, the definition is not complete. Fine? Simplest possible example. Huh? R? R2. Why do you want to go to R2? Simplest possible example is what? Come on. I mean, don't give me a trivial example. The simplest that way is just 0. That becomes a trivial example. Give me something which is interesting and which is the simplest possible. Sahil, 0 is not interesting. Something. Huh?
Polynomial of order 0.
That can be put in a better way.
R.
Yeah, it is R. But then, again, see, I said whenever you think of vector space, 4 things should come to your mind.
Field can be integers.
So V is?
V is R and F is Z.
The simplest I would still say is F is R. F is R, and the set of vectors is R, the field is also R, and what is vector addition? Vector addition is your conventional addition, right? Conventional addition. And conventional multiplication. That is a scalar multiplication. In this case, what is a vector? Huh? What is a vector here? Vector is a point, isn't it? A real number is a point. It's just, so that is why I said remove your notion of vector. Whatever notion of vector you have in your mind, remove it. After attending this class, never again say that vector is something with a direction and magnitude. No. So, vector in its most abstract sense is any element of the set V that you define. Here you have defined V as R. So, in this case, vector is a real number or a point on a line. In this case, it is a point on that horizontal line on your x-axis, right? In this case, vector is a real number. So, I am showing you different instances of vector, okay? So that that notion of vector goes away from your head. Whatever notion you have in your mind should go away. So what about this? R, okay, as he said, as Shivam said, is this a vector space?
What is that then?
Z, a set of integers. Okay, so this, then R, Q plus multiplication. Are these two vector spaces? Q is a set of rationals. This is a set of rationals. Z is a set of integers. Are these two vector spaces? Huh? You are having some doubt, Akanksha. Is everyone convinced? See, you take an element. Why should Z be positive? Vasudeva, why should Z be positive? maybe there's nothing called as a negative field.
Yeah. Ma'am.
Yeah.
It is a multiplication point, it's like a magnitude thing like that.
Be careful, be careful.
Okay.
No, the thing is, see, out of these two examples, RZ plus multiplication and the other one,
Okay.
do you think that both of them are vector spaces? Are both of these vector spaces?
Yeah, first one is vector.
What?
One RZ addition multiplication is a vector space. Yeah. One R is a point vector.
No, no, no.
And the field are not correct, I think.
What?
Field is correct because we can add and multiply. We can perform operations with Z and Q. We can perform addition and multiplication. So we can consider them as fields.
Vector.
But division cannot be possible because number two will not be
Yes. You cannot divide in Z. Can you divide in Z?
Oh,
Z is not a field.
by zero.
No, no, not even. See, if I take 2, does 2 have a multiplicative inverse? No, you don't have a multiplicative inverse in Z. Z is a group under addition, but Z is not a group under multiplication. Right? So in this case, it's not possible. But this, yes, because in Q is a field. In Q you can divide.
Okay.
See, I said that the field is a place where you can add, multiply, divide and subtract. So if you look at Q, in Q you can divide, but in Z you cannot divide because multiplicative inverse means if I take a number A into B should give me 1. So there is no number B in Z because if I take 2 into half only can give me 1. There is no half in Z. Since there is no half in Z, it means that there is no multiplicative inverse in Z. So Z cannot be a field. Z is a group, but it is not a field. What about Q anyway is a field because in Q you can also divide. But then why did I say initially when Shivam gave this example, I said let us go for something simple. So does it look like a simple field for you people? See, if you look at RQ plus and multiplication, it is not it's actually quite a complicated vector space, okay? Why I say that it is a complicated vector space is later on we will see, if you look at there's something called as a dimension. So if you look at this is an extremely complicated vector space in that sense. How it is, I'll come to later when we discuss about bases. This is actually quite an,
in Q also means the multiplicative inverse is not possible.
it is there. Any number you take, any m by n you have, n by m.
Number will be irrational.
No, there is no irrationals in Q, right? Q is a set of rational numbers. Q is a set of all numbers of the form P by Q, where Q is not equal to 0.
Okay.
See, Q is a set of rationals. Set of rationals means it is a set of all numbers. So I'll write it as set of all,
Pi by Q.
m by n not equal to 0, and m and n are integers. So any m by n you take, n by m is going to be the multiplicative inverse. Right?
Ma'am,
Yeah.
multiplicative identity means if we multiply with the identity means we will get the same vector now.
No, multiplicative identity is defined in the field. So when you yeah, so see this 1, or I'll call it as E. E is, say alpha is an element of F, alpha into E is equal to alpha. That is multiplicative identity. You take a number from the field, multiply it with the multiplicative identity, you get the same number back.
Okay. Ma'am, in our example, if we take alpha equal to 2, then
Alpha, no,
we should have E belong to that particular field. Okay.
yeah. Confused? What is
Yes,
it?
yes, ma'am.
Huh? Little bit. What is the confusion?
Ma'am, you said if we take alpha equal to 2,
Huh?
then
No, I'm talking about Z. See, suppose take Z. What does Z contain? Z is numbers of the form like this, and then -1, -2, so on, right?
yeah.
So if I take a number 2, 2 into x should be equal to 1, right?
Ma'am, you said we should get alpha na again.
No.
Alpha into E equal to alpha.
That is existence of identity. Identity is there, but inverse is not there. See, the number identity, see, let us say identity is E. So what, for any element alpha element of Z, alpha into E should give me alpha. So it is present, identity is present, identity is 1, but there is no inverse. You should also have alpha inverse such that alpha into alpha inverse gives me E back. So in this case, 2 into alpha inverse should give me 1, which means alpha inverse is half. Half is not an element of Z, so there is no inverse. Identity is there. Yes, identity is there, inverse is not there. No inverse means you cannot divide here, right?
Yeah.
So since multiplicative inverse doesn't exist, it is not a field. Is that clear?
Yes, ma'am.
So R over Z plus dot is not a vector space because it's not a field, but R over Q plus dot is a vector space because Q is a field. But it is actually a, I mean, as we will see later on, this is a very special field, a special vector space. We will see what it is. Any other example? I'll write, tell me whether it is a vector space or not. Set of all so periodic function is something like this, f of t plus n t naught is equal to f of t. So what I am saying is, so this is my vector v. V is set of all f such that this is true. Okay. And my the field is R. Addition is point-wise addition. And scalar multiplication is scaling. Just scaling by a real number. Understood what is the set of vectors? In this case, what I am saying is,
Sin omega and cos omega.
I mean that there are two sample functions.
Multiplicate.
What would be omega? Sin omega, so you can say,
Multiplication.
yeah, sin omega 0 t, cos omega 0 t, you can say omega 0 in this case will be 2 pi by t, t pi by t naught. What I am saying is, you take all functions which repeats at t0 time period. This means, see, the meaning of this equation is, I am considering all functions which repeats at an interval of t naught. The function repeats itself. It's a periodic signal. Anything periodic, right? I mean, sample function can be something like this. I can have in this side also, like this. So this duration is t naught. It repeats in t naught time. This can be one sample function. Another sample function can be, say, as you said, sinusoid. Again, this duration is t naught. Collect all such functions, whatever be the shape, doesn't matter. You collect all possible functions who has a period of t naught. That means after every t naught seconds it repeats. Put all those functions in a set. Define the field as real. Addition is point-wise addition. Scalar multiplication is scaling by a constant. Is this a vector space or not? Think and tell me.
No, ma'am.
Why?
multiplication by 0 is not possible.
What?
It will give a periodic function,
Huh?
but not of time t naught.
No, 0 can be thought of as periodic with any period actually. So it can be thought of as periodic with t naught also.
No, ma'am. I'm taking the scalar as 0.
That is fine, right? If you have the function as 0.
When
Function as, see, if f of t is 0, f of t can, it can have a period of t naught also.
No, ma'am. The function is of any function which is periodic.
Yes.
Means not 0. Any function but 0.
No. The thing, what I am saying is, if you consider the function 0, the 0 function can be considered as periodic with period t naught, any period.
Okay.
Yeah.
The time is not fixed.
No.
Period is not fixed. Okay.
No, period is t naught, but what I am saying is, when you have the signal as 0, I can think of it as periodic with a period of t naught also. I can assign whatever period I want to the signal 0. It doesn't, I mean, nothing stops me from doing that. Because it is anyway 0 everywhere, right? So I can say that it repeats at t naught. I mean, it is not fundamentally incorrect.
Yes.
So that being the case, suppose you add two signals with period t naught, what will you get?
It is not a vector space.
Why not?
Because if we take two signals with n is equal to 22 and n is equal to 7.
No. Definition of what is the definition of period? Period is the smallest. That means for n is equal to 1, whatever number comes is the period. That I am calling as t naught. So every signal has a period of t naught. So writing f of t plus n t naught is equal to f of t is a formal way of expressing it. It means that the signal has a period of t naught. Every signal in this set has a period of t naught.
He has considered two different periods.
No, it is same period, t naught, right? I am saying t naught is fixed.
But I am wearing n.
No, that's what I am saying. N can be anything.
Yes, ma'am.
That is a formal definition.
I am taking n.
No. You're not understanding that. The thing is, see, whether I look at t naught or I look at 2 t naught, once t naught is a period, then 2 t naught, 3 naught, any n t naught is also a period. You take the smallest value, which is t naught. So when I say that a signal is of period t naught, it means the smallest repetition is at t naught. So there is no point in considering two different values.
If we add two periodic functions, that is not that need not to be.
When the two periods are different. If you are adding a signal with period t1 and period t2, there is no guarantee. But when t1 is equal to t2 is equal to t naught, it is always guaranteed that you will get a periodic signal. You add two periodic signals with the same period, you will still get a periodic signal of the same period. So this set V is going to be a vector space. V over R plus dot is a vector space. Because if you are adding two signals having the same period, you will get another signal with the same period. So in this case, your V R plus dot is a vector space. How can you make it not a vector space? By slight change of definition, I can make it not a vector space.
By making the time period fixed.
No, time period fixed is what makes it vector space. See, suppose I consider.
If the time period will be fixed.
Yeah, t naught. See, I said the time period is fixed as t naught here. See, think like this. I'm adding these two. I add the square wave and I add the sine wave. Remember that at every t naught the same shape comes. So once you add, again you get the same shape at every t naught, right? So whenever you are having the same period, you add two signals, you'll still get a periodic signal. That is because it keeps repeating at the same instant. At every t naught it repeats, so you'll get the same shape. But suppose the two periods were different. One signal had a period of t1, the other signal had a period of t2, then it is not always guaranteed that the sum will be periodic. So suppose I redefine my set V as the set of all periodic signals, then it is not a vector space. Right? So do one thing, think about it. We'll continue in the next class. Because I have to leave this room now. So any more questions, you can mail me.
Okay.
Mail me, or I'll do one thing, I'll open, there is something called a Slido which I use. So I'll open a Slido link and share with you. So you can post your questions there so that everyone can see it. Fine? Yeah. Okay then, I'll sign off for now and I'll tell you when the next class is. Okay, bye.